Thank you. Good afternoon, everyone. Thank you for attending this AIS seminar and participate in my section. So my research is, Dr. Mahdi said, is primarily focused on three areas: development of wireless sensing network and IoT system for both biomedical and industrial applications, applying ultrasound for orthopedic and rehabilitation applications, and applying artificial intelligence on medical imaging, development of prediction models, and analytical engine. So before I present some of my projects, I would like to acknowledge the funding agency in this slide, which have been providing funding to my research work and support all my graduate students and trainees as well. I would also like to acknowledge the Edmonton Scoliosis interdisciplinary group that provide clinical data for lots of my project related to scoliosis, and also this team includes some surgeons, faculty members from different departments, neurophysiologists, nurse practitioner, clinical engineer, auditors, as well as I would like to thank you my research team. They did hard work on making the project going. Also, I would like to acknowledge the AI supercomputing app. Although I'm the principal investigator, but right now it is running separately. So it has its own director look after the operation. So the Isaac, this is the new name that they developed, called the Isaac, and it is housed at the eServe basement on the room 128. And under there, under this facility, they have a fast compute node that allow you to apply all kind of AI application into it. And it will save you a lot of time if you need to do some training. So this facility is available for university people as well as industry. So if you have project and you interest to using their facility, you can contact them. So I provide the web page address already. So you can contact them directly, and then they will help you to allocate some of the virtual machine using part of their facility, help you to run your training model. It will save lots of time. So I have a model that one of my students tried to train on, even though on a desktop, it took about 8 hours. But running in this facility, it only takes 15 minutes. So it really, really saves a lot of time if you have a huge amount of data and you need to run and you need to perform some AI project applications. Okay, so then before my team, I have 3 team members who are going to present their projects. But before they present their individual project, I also want to mention in my lab, I also have other projects going as well. So one is the wireless implant sensor. So this system built on a special wireless communication protocol using 400 to 405 megahertz. And in this project, we spin off to develop some energy harvester based on motion. So the whole system can be embedded inside the body and allow you to communicate outside and inside. So the sensor will be embedded inside the body, and we have a base station outside, and we can using the wireless to communicate between the two devices and getting the information. The next project that I would like to talk about is the posture monitor system. It was initiated from the Edmonton Scoliosis Clinic 10 years ago. And of course, we've been upgraded and making changes in which the orthopedics first asked, can we build some monitor system that can monitor the children's posture and provide the feedback? The reason is some of the children, they have spinal curvature. If you teach them, they will be able to correct themselves instead of doing some brace treatment or surgery. So exercise is another type of treatment that can help children. They have the mild or moderate curve. They may help them to correct their posture. So they come to us and then ask us, can we build some wireless monitoring system? So we build a network. One of my master students also test the network and already been used by many patients already. And some of the patients, they get a good result on their curvature. So this is one type of the technology that we spin off from the lab, go to translate into the clinical use. I also try to develop using the 3D printing technology to print some braces for the kid. They have spinal curvature. So as you can see in here, this is a patient that stand on a stand, and then we are able to scan their posture and generate the posture based on the software, and then develop the brace using the 3D printing technology. Now, the advantages of using the 3D technology to print a brace is the cost is lower, much lower. If you are making a brace in Edmonton here, each one costs about $2,500. So they will charge $2,500 per brace. And the material and the for printing a brace is only $100. If I print a brace, I only need $100 material, and the time, like of course, it will take longer time to print another entire brace. It take about 40 hours, but it's still cheaper than from manual manufacturing. So that is one of the goal that we would like to move on to printing the brace using the 3D technology. And also there's already collaborate with a company in Vancouver. They interest in the technology because they provide the scanner and we are providing the brace for them to treat the patient have scoliosis. Another commercial product, this is also initiated by a company from clinicians that they would like to develop a computerized hot and cold sensation devices that allow us to do assessment on patients they have diabetes. So some patients, they have diabetes, they may lose the hot and cold sensation. In the past, therapists always using the test tube, putting some hot water, some cold water, and then ask the patient to close their eye and then test it. However, because the hot water and cold water will change the temperature, and you are not able to maintain the constant temperature. So then the company is interested to see, are we able to help them to develop a commercial product that can using the electronic technology to generate heat and cold, and then allow them to maintain the temperature in a constant for long periods of time during the assessment. So that is a commercial product, and we are in the final stage right now. So almost helping the company to manufacturing this product for their production. Now, another project that we are working on is also with company as well. It is from a company in Vancouver called the Curious Ultrasound Mobile Ultrasound Company. So they have the portable ultrasound product. However, when they scan the ultrasound, you still only get the static frame. So I partner with this company and convert this machine into a 3D portable wireless ultrasound system. So when you scan on a patient, we have a software automatically stitching the images together. And because we putting a position and orientation sensor, a 3D position and orientation sensor into the system, that allow us to reconstruct the image in 3D. We can reconstruct in 3D images. We also able to reconstruct this image as I show in the diagram here within 2 seconds. So almost instantly. So when you scan, you are able to see the outcome in real time. So we also apply this in the scoliosis clinic as well, because traditionally they're using X-ray. We are the pioneer teams in the world that we introduce the ultrasound to scan scoliosis patients. So we received lots of awards and published lots of papers on this area. So we still continue working on this, and we hope to make this product available so that it will be cheaper, because compared to the X-ray system, the whole system will be much cheaper, and also it will be safer. So no ionizing radiation to the kid. So this is one of my key project as well. Now, I'm going to turn it to my team member. One is like my master student, Andi. She's still doing the master program right now on the 2nd year, and she's going to present an intelligence IoT system with AI analytical engine. So Andi, are you there? So I need to.
Yeah.
Can you control the screen? Yeah.
Oh, yeah. So my name is Andi, and I'm from electrical and computer engineering, and I'm gonna talk about an intelligent IoT system with artificial intelligent analytical engine. So let's start with the IoTs. So IoT is a system of interrelated devices and the ability to exchange data wirelessly with no human-to-human or human-to-computer interactions. Using an IoT system avoids the cost of massive cabling and cable installation. And as you can see on the figure, its architecture mainly consists of 3 tiers: the nodes, the gateway, and the cloud. So, and different multiple wireless communication protocols can be used to transmit data from the node to the gateway. And the nodes are usually embedded with sensors that's responsible for collecting data, and the gateway is used to link the node and the cloud, where all the data will be stored in the cloud for further analysis. Yeah. Stress and strain sensing could be very useful in many areas, such as the structural health monitoring. And for example, sensors are mounted on the pipelines to observe the structure continuously and predict the failures. It can also be very useful in medical areas, such as the gait analysis and the seat monitoring. So by monitoring the working pattern and the sitting pressure distribution, the clinicians could analyze those data and to decide the treatment further. The last figure shows the brace for scoliosis treatment. Stress and strain are measured to determine the brace wear tightness. So for both application A and D requires long-term monitoring. In that case, a large amount of data will be collected. However, for a project that is powered by a rechargeable battery, they have a limited power and memory size. Traditionally, data are collected all the times, and however, limited power and memory size will cause a problem. In that case, an optimized data acquisition system is proposed. A dynamic sampling approach will be applied when there is an abnormal change in stress and strain is detected. The sampling frequency will be changed to a higher one, and to further reduce the memory size, the system will put into the sleep mode while the data is not collecting. So the objective of this study is to design and validate an intelligent IoT system, which includes an optimized data acquisition system, as well as an AI analytical engine to monitor the three-dimensional stress and strain. So this figure shows the center that's developed by Dr. Musa Group in Mechanical Engineering Department at University of Alberta. So there are in total 20 strain gauges typed sensing elements, while 16 of them will be used to extract three-dimensional stress and strain information with temperature compensation. And when the sensor is compressed or stretched, it will experience a change in resistance. And according to the Ohm's law, by supplying a constant current, we can convert this change in resistance to a change in voltage, which can be measured by this which can be measured and recorded by the microcontroller. Here is the block diagram of the sensing cells. Its mainly consists of 5 sections: the sensing element, the power supply section, the A to D converter, and the flash memory to store all the data, and the microcontroller with built-in Bluetooth Low Energy. Here is the flowchart for each sensing node. We will start with the initialization, collecting the baseline value and calculate the reference threshold based on the baseline value and enter the sleep mode. After it was picked up from the sleep mode, the microcontroller will read the ADC value to check if it's within the reference range. If yes, then we will use a lower sampling frequency. If no, we will change it to a higher sampling frequency and store the data, go back to the sleep mode, and wait for another wake up. Here is the network topology. Network topology is arrangement of elements of a communication network. There are five types of communication. As we mentioned before, the gateway is used to link the node and the cloud. However, when the distance between the node to the gateway is larger than the maximum distance, a router will be needed to extend that distance. And the communication between nodes is also necessary, since due to the BLE configuration, one BLE device can only connect up to 7 devices in total. In that case, when there is more than 7 nodes wants to connect with one router or gateway, you will need another node. You will need another node to be put in between. Use it as a rotor. So here is the current results. The top two figures shows the sensing board and the data acquisition system. And the current consumption of it has been tested. In normal mode, it consumes 4 milliamp, while it only consumes 5 microamp in sleep mode. However, in transmission mode, it will consume 20 milliamp, which is much higher than 4 milliamp. And the bottom two figures shows the rotor I'm using and the gateway. As you can see in the figure, the rotor will use a bigger antenna instead of a cheap antenna. In that case, it will have a much larger transmission distance. In this figure, which shows the maximum transmission distance between the rotor to rotor, node to rotor, rotor to the gateway, and node to node. As we can see, since the rotor has a bigger antenna, the transmission distance is much larger than others. So I'm currently still working on the investigation of accuracy of the A to D converter and studying the signal-to-noise ratio of the sensing element. And the analytical engine is still under development. So, and Dr. Low will talk about an application using artificial intelligence. So I'm going to...
Yep. So, Andy, thank you. So one of the applications that we aim for develop the IoT system is for, so Andy, don't control it. Don't control the mouse. Yeah. So one of the application is to investigate the effectiveness of the brace treatment for children with scoliosis. As you can see in here on the X-ray, this patient have a spinal curvature. When she wear a brace and her spine becomes straight. Now, in order to make the brace effective, the patient need to wear enough time as well as enough tightness. So if they just put it on and wear it loosely, they may not be effective. So one of the applications that we are thinking about is to put in the IoT system, put inside the brace, monitor how much time and how tight the patient wear. And also, once we collect enough information, we are going to build a machine learning engine. So that will allow us to optimize the treatment protocol. So based on that, we will be able to tell the patient how tight they should wear their brace and also how long they should wear the brace. Of course, wearing the brace is restrict their daily activities. So a lot of time, the children doesn't like to wear the brace. So guess we would like to get the information and then provide the analytical engine so that the orthopedic surgeon or the orthotist can get this information and provide the optimization treatment protocol to the patient. So to improve their quality life as well. Now I'm going to pass to Jason before I need to stop share. So Jason is going to present using the machine learning to measure on the ultrasound images.
Yeah, awesome. Thank you for the introduction. Hi, everybody. Can everyone see the screen and can you hear my voice okay?
Yes.
Okay, perfect. Thank you. Yeah, so as Dr. Lau said, I'm here to present on my research in applying machine learning to automate measurements on 3D ultrasound images for children with adolescent idiopathic scoliosis, or AIS as we typically call it. And so AIS is a condition found in adolescents where their spine has a lateral curvature coupled with a vertebral rotation. And so you can see in the middle image here, a model of a spine with scoliosis. And so you can see that the spine isn't straight. And also particularly in the lower region of the spine, you can see that the vertebrae themselves are rotated a bit to the left. And so to give you an idea of what it looks like from a clinical perspective, here's an x-ray of a patient with no scoliosis. The spine is very straight. And on the right here, you can see one of moderate scoliosis with a typical S-shaped curvature. And so yeah, I showed x-rays here. That is very typical for clinical diagnosis of scoliosis. But recently, as Dr. Lau has said, we were trying to push for ultrasound as an alternative imaging modality for AIS. And you can see an ultrasound on the right here. And so from a clinical perspective, there are really three major factors that come into play when trying to decide between the two modalities. So the biggest one, also Dr. Lau went over, is that ultrasound is radiation free. So one study found that women who were diagnosed with scoliosis as children were found to have a 70% excess risk of dying from breast cancer due to all of these radiographs they underwent. And so really we want to try to minimize the radiation exposure because it clearly has an impact. Second of all, ultrasound inherently provides 3D information. So I mentioned that it's a 3D deformity. X-ray by itself, one scan only provides 2D information. So one X-ray scan can provide this view here, but an ultrasound scan provides you a full volume, which means that you can get that same view on the right here, but also the sagittal view or the lateral view, and the individual transverse or axial views as well. And so that's really helpful in giving us a way to measure the deformity accurately and directly as well. And finally, the major drawback of ultrasound is that it is more time consuming to measure. So X-ray is quite common, so it's quite intuitive for just a regular layman to look at. For ultrasound, it's a bit different. You really need to be trained to know what to look for and therefore trained to know how to measure accurately and reliably as well. And so that ends up being quite a barrier of entry for clinics to adopt ultrasound for scoliosis diagnosis. And that's kind of what we're trying to remedy here. And so that brings me to machine learning. So machine learning is a field, it's a subset of artificial intelligence that consists of taking in labeled data, learning from that data, and then generating predictions based off of what it learned. And so typically, common uses for it in the biomedical field is task automation and improving diagnosis, and also providing insight into conditions that we wouldn't otherwise have with just pure human judgment. So it's been helpful in that regard. And so that brings me to my objective, which is to use machine learning to automate AIS measurements on 3D spinal ultrasonographs. And this is all for the sake of making ultrasound more commonplace in clinical scoliosis diagnosis. And so really what we want from our final system is we get our ultrasound scan of a patient with AIS. We input that into a trained machine learning or artificial intelligence model, which then outputs the relevant measurements. And so the relevant measurements for our case is the Cobb angle in the coronal plane or the posterior anterior view, the kyphosis in the sagittal plane or the lateral view, and finally the vertical rotation in the transverse or axial views. And so I've been focusing on the Cobb angle, so I'll be reporting on some of the methodology and results that I have for that so far. But basically, our measurement approach consists of using the center of laminae method, essentially identifying these 2 points on the vertebra for each, identifying the 2 points on this vertebra for each vertebra in the volume, and that consists of identifying these orange dots on the ultrasonograph here. Once we have the laminae, we can then pair them up according to which ones are on the same vertebra, and then take the steepest angles and measure the Cobb angle. And so really our method hinges on identifying these laminae, and that's what we use machine learning for. But before I get into the machine learning, one important step before that is pre-processing, just to make sure the inputs are as clear as possible. So essentially we start off with a raw volume. Our first step is to improve the clarity of the volume. In this case, removing the ultrasound reflections from the skin that make the volume noisy. And so the effect of that is most apparent in the middle here. You can see this dark curve, it really pops up more. So this is the spinous process curve, and that's particularly important that it's more clear because we need to use that to get our region of interest. So we identify the spinous process curve using a thresholding algorithm, and we get that red curve here. And then we can crop around that curve to narrow our search area. That makes the model predict better, just makes it a bit easier for it to find the laminae. And so now that we have our process volumes, we can now start looking towards training the machine learning model. So in our case, we use a convolutional neural network, very common for image and volume inputs, and really has been used in a lot of research. And we labeled 70 volumes. We use that as our training set, and then we train it for roughly 24 hours or 1200 epochs to get outputs like this. And so now we have a way to segment the laminae. And so we conducted a feasibility study to really investigate whether it's sufficient for ultrasound measurement automation. And so what we did is we selected 37 test volumes from our local database, and then we semi-automatically measured them and compared them with manual measurements that experienced observers made on the same ultrasound volumes. And so that semi-automatic procedure consisted of getting our network outputs and then pairing them up manually and then doing that same angle measurement that I talked about before. And so in terms of results, out of the 37 cases, there were 73 curves detected, and you can see some example outputs of these semi-automatic measurements on the right. 66 of those curves were detected, with 74% within clinical acceptance, in this case within 5 degrees of the manual measurements, and the mean absolute difference was 3.7 degrees. Overall, the measurement time for the semi-automatic procedure took around 30 seconds. Compared to the manual time, it takes roughly 90 seconds, so it did improve upon that. And then here's a scatter plot just to visualize the results a bit. Basically, these red lines are the clinical acceptance bounds, so we really want our blue dots to be within those bounds. All right, but in conclusion, machine learning was used to help measure the Cobb angle, where we used a convolutional neural network to help automate lambda detection. And then results are promising. They showed feasibility. As I said, we got 74% of measurements within clinical acceptance. And in terms of future work, we hope to improve the accuracy and also perform a larger clinical study to further validate the results and also to develop code for full automation to make ultrasound more commonplace in scoliosis clinics. And with that, I thank you all for listening, and I will hand it off to Andrew, my colleague.
Thanks, Jason. Just gonna share my screen. Everyone can hear me okay? Great, alrighty. So my name's Andrew. I actually just finished my PhD last year with Dr. Lau. And so I'm just presenting some of the stuff that I did with him. He invited me to talk about the 3D ultrasound navigation system we developed for pedicle screw insertion in scoliosis surgery. Let's see, is it moving? There you go. So scoliosis is a three-dimensional spinal deformity, as Jason said. And I really like this picture because it really shows how severe the deformity can get, even in adolescent idiopathic scoliosis, which is the most common form. And so these patients would typically need surgery to correct their curvature. It's a relatively common surgery, being the second most common pediatric orthopedic surgery from a major US database. And the surgery involves the patient being placed prone, so face down. The spine is opened up, and then they straighten the spine and attach these rods longitudinally so that the spine is held in a straight position. And they attach these rods to the spine using screws. Now these screws go from posterior to anterior through this narrow pedicle here into the vertebral body. And you can see right here is the spinal cord, and you have nerve roots that go above and below the pedicle. And so accuracy is very important. You have to make sure that you're not going to cause a neurologic injury when you're treating scoliosis. And so in the past, freehand methods have worked very well. Surgeons will landmark where they want to put the screw and then use handheld tools to guide the trajectory through the trabecular bone into the vertebral body. Now, in recent years, navigation, so CT and fluoroscopic navigation has gained popularity. That involves scanning the patient in the operating room so that you get a live image, and then using motion capture to display surgical tools on the same screen so that you can actually get that visual feedback. Some of the problems with this, though, is that guidance can be very expensive. It's bulky, so you have to wheel these large machines into the OR, and it does use ionizing radiation, which we want to minimize in our pediatric patients. And so our question was, can we provide image guidance using 3D ultrasound to reduce this ionizing radiation, reduce the need for these large machines that have to be wheeled in, but also needing to achieve the same accuracy and even better processing time if we can compared to these navigation systems. And so our 3D ultrasound concept, first of all, involves using ultrasound to provide a 2D planar surface of the spine. So you can see that this is the bone inside water, and the reflection looks really nice. Right? You can see the surface very well with ultrasound. You can't see anything deep. You can't see the pedicles themselves. But what we can do is take these surface images and pair them up with motion capture information, so position orientation, and reconstruct the entire surface. This surface will then be localized in the 3D space, in the 3D navigation space. And we can use this kind of like a footprint to attach a foot onto it. So you attach the full pre-op, some sort of pre-op 3D model onto this surface using image registration, so that on the screen, you can actually see the entire 3D model, including all the interior structures. So right now we're using preoperative CTs, but we'd want to use other 3D modalities if possible. Once the vertebra is displayed on screen, it would work similarly to other navigation systems where you have the model on screen and you have your surgical tools being tracked on that screen. So in terms of kind of how do we do this, we have our ultrasound producing the images. We have our cameras giving us position orientation, and they're both streaming at the same time. So all of the frames are matched together. So the images are matched with the position orientation information. We binarize these images to reduce the amount of information that needs to be reconstructed. And then we use a very basic nearest neighbor pixel method to reconstruct all of these pixels into the 3D space. So you're just taking every slice and placing it into the 3D volume according to that position and orientation. We get this nice 3D ultrasound surface, and then we need to do the registration. So we register the CT model onto this ultrasound surface. And we have two steps for that. Number one is to use the symmetry of the vertebra to pre-align the two in terms of orientation. And then we take the rough centroids to draw them closer together. And then we use an iterative closest point registration algorithm, which is commonly used for point clouds. And so we use that algorithm to do all the fine tuning of our registration algorithm. And so we have our CT in green here, and then we have our pink ultrasound with some artifacts from stray reflections. And the white is where the CT is being registered to our ultrasound surface. Then we take all our transformation matrices from this registration process and apply it to a model so that we can actually display it on a screen. So we have, as equipment, we have our motion capture cameras that we used. We have our ultrasound transducer. Any kind of transducer could be used. We just attached reflective markers to it. And then we made our own reconstruction and registration algorithm and our own kind of navigation display in the Unity 3D environment. So you can see here, this is a registered vertebra, and then again, the surgical tools right on top. So in order to validate our system, we use 3D printing. So we used a PolyJet 3D printer to get much higher accuracies for our vertebrae. We segmented and extracted a vertebra from a CT scan. And then we did a few modifications for our study. First of all, we added a Lego mount. So there's actually a mount down here that allows it to be mounted onto a Lego pegboard so that we know its orientation during the study. And we also include these holes that go through the pedicles. We know the trajectories that these holes go through, so that when we place this probe, the surgical probe, into these holes, we can make some measurements on the trajectories and the position. So in our study, the phantom would be submerged in the water bath. In the OR, the cavity, the spinal cavity would be filled with saline, and we tried that in the OR a few times. We mount this phantom to the pegboard, and then at the origin, we tested 9 different vertebral levels for this patient. And then 7 orientations. So we oriented the vertebra in roll, pitch, and yaw in both directions, and then as well as neutral. And then we also randomized placing it at the corners at different heights, and also at different orientations for all 9 vertebral levels. So in total, we had around 680 measurements for our study. We would scan the phantom, display it on the screen, and we insert the probe. And so when this probe is inserted on the screen, you can see that there's this multi-ringed surgical tool here. And we use these multiple rings to make measurements as to how inaccurate our system is. So each of these rings is around 0.5 millimeters in width. And so we can make some measurements on how much overlap this ring is with the actual pedicle hole on the vertebra itself. In terms of trajectory, we just displayed the probe trajectory from motion capture cameras and compared that with our theoretical values that we should have as we designed it. So our target accuracy was 1 millimeter and 5 degrees, and we wanted everything to be within 1 minute of processing time. And so to give you just some of our results, we were pleasantly surprised that we were able to get good accuracy. So our average is around 0.4 millimeters, and 95% of them were within 1 millimeter. And then in terms of trajectory, we were able to get an average around 2 degrees with 99% of them within our target of 5 degrees. And then processing time-wise, the total time, including the scan, was 23 seconds. The scan itself takes 14.5 seconds, and then the processing time for reconstruction, registration, all of that is around 8 seconds. So it's very, very fast. We're pleasantly surprised with that. And so we have shown that, at least for our phantoms, we can achieve faster processing times and better registration errors than some of the larger surgical registration studies that we've seen. But in the future, we certainly want to increase the robustness of our registration. So we'd want to use artificial intelligence to pre-align these vertebrae more robustly. And secondly, certainly we want to do a probing study with surgical residents on either a porcine spine or a cadaver spine before we want to try to move forward to commercialization.